There's one other common type of coding that you're probably that you'll also see in the literature, or you may read about, which is called orthogonal coding. Now the book doesn't get into this, but I just wanted to introduce it because you may come across it or hear the term if you're reading the literature. And with orthogonal coding, you're still doing basically the same idea. If you've got 4 groups, you're going to have to make 3 new codes, three new variables that will reflect that overall effect of all the groups. Your R squared for orthogonal coding is going to be exactly the same as the R squared if you did dummy coding or effect coding. The how significant its F-test is going to be exactly the same. But orthogonal coding is different in that instead of comparing everybody to one group or every group to the mean of the means, orthogonal coding is asking very specific questions between the groups. And it does it in a way that those questions are what we, in geek speak, are orthogonal. It just means they're uncorrelated with each other. The issue here, it's kind of subtle, but the issue here is if you've got a lot of codes, if you've got a lot of groups, we think back to the type 1 error, that 5% of the time you're going to say, oh, I've got a significant effect when you don't. There can be, kind of related to all this, if I'm looking at how does everybody compare to one group, if by chance, or by design, that's the lowest group or the highest group, the fact that one effect is significant, probably others will be significant as well. The comparisons, the questions are related to each other because they're all coming back to the same referent group. So if my group is significantly higher than the referent group, and your group has a higher mean than my group, your group's probably going to be significantly different from the referent group as well. They're not independent. The questions are all kind of correlated with each other, which can inflate your chance of a type 1 error. You end up, you pick the most extreme group as the comparison, and there might be a whole bunch of significant effects, just because the way they're all related to each other. Knowing one effect tells you a little bit about what you might expect to see for the others. In orthogonal coding, that's not the case. Every coefficient is completely unrelated. If this coefficient is significant, what it's asking is completely unrelated to what that coefficient's asking and testing. So it makes it cleaner in that way. We've used the term orthogonal is kind of a statistical term for, actually it's kind of, things are at 90-degree angles with each other. In kind of a statistical space. It's kind of cool. But it's another way of saying that they're unrelated, uncorrelated, more or less. Again, it helps minimize that chance that there'll be a lot of significant effects just because those dummy codes or effect codes are all correlated with each other. To kind of see how it works, probably the easiest way is to actually give you an example. So let's say I'm looking at 4 different types of curriculum, same as last week. A standard curriculum, an intensive curriculum, a math-focused, and a language arts-focused curriculum. So I got 4 groups. We know that with 4 groups, if we do dummy coding, 3 variables, we can only make 3 dummy codes. The last one's going to be redundant. If we do effect coding, it's the same thing. And it's the same with orthogonal coding, even if it's a little less obvious. 3 variables, those 3 variables will tell you exactly which group you're in, so you can't add a 4th. To make the coding, orthogonal coding can be complex, and coming up with the right values is a little messy, and software will help you do it. And again, I think that's maybe one reason the book doesn't go into it all. But on a conceptual level, what you can think of is it's looking at specific comparisons between groups. So with kind of a very simple orthogonal comparison with 4 groups, right? We have 3 variables. One variable could test, is the standard group different from the intensive language group? And the second code might then test, is the math focus different than the ELA focused? Notice it's completely different variables. Let's say this one says, oh, standard is a lot more higher than the, or let's say the intensive scores are a lot higher than the standard scores. Knowing that intensive is much better than the standard, does that give you any clue to what you're going to see as ELA better than math? No, it doesn't tell you any. You have no reason to think. Because this might be a huge difference between those two, but that doesn't tell you anything about what's going on here. That's this idea they're uncorrelated. And if we look at the coefficients, when we make those orthogonal codes, if you correlated those coefficients, they're going to have a correlation of 0. The third one then, to be unrelated to the other two, the third one then has to ask a question that if I know which one's bigger here and I know which one's bigger here, it still doesn't tell me anything about the, I don't have any, it doesn't tell me anything about this final comparison. A way to do that would be you combine is the standard and intensive curriculum, so kind of more general curriculums, one standard, one might be just very intensive, compared to a focused curriculum, the math and the ELA curriculum. So you're combining those groups. So here you're saying the standard versus intensive. Here it's math versus ELA. Here is standard and intensive combined. Is that better than math and ELA combined? And it may not be obvious at first, but if you think about it, knowing that intensive is a lot better than math than the standard still doesn't tell you that it's necessarily going to be better than these two combined. And same if I know that ELA is much better than the math focused, that tells me, well, in this group, these ones are really high and this is really low. But that doesn't tell me, that doesn't give me any clue as to whether combining them, are they going to be better than the other two? It's just another way. It's kind of a little weird. But the outside of being uncorrelated, so it has that statistical advantage, what it does is notice it's asking different questions than than you get from dummy coding or effect coding. So you might be looking at your groups and thinking, well, I don't want to compare everybody to the standard curriculum. And I don't want to compare everybody to the mean of the means. I want to compare this group, these two groups, and I want to compare those two groups. You can do that. Orthogonal coding gives you a way of doing that, probably. But you have to just kind of follow the rules. Because let's say I cheated, or I said, I'm going to compare standard intensive and math and ELA. And then you say, and the other thing I'm interested in is, I want to compare math to the standard. If you made another code here that was math versus standard, it wouldn't work. You would no longer be, those three variables would no longer tell you which curriculum you're in anymore. This is a good way of explaining. I need to remember this. This is a good way. I may not be explaining it good, but it's in my head good. That what orthogonal coding does is it answers those specific group comparisons you want to make within your groups. But the key is, in order, outside of making them uncorrelated, in order to reflect whatever that underlying construct is, what curriculum are you in, it has to follow those rules. If it doesn't follow those rules, whatever, you can make three codes, three variables, but they're not going to be what curriculum are you in. They're going to be kind of a sloppy, gooey, little kind of related to curriculum but not curriculum variable. So if you've got these sorts of questions, I want to compare these two groups. I want to compare those two groups. Orthogonal coding can do it. And that last question, in this case, you may not be as interested in you two versus, you guys combined versus you guys combined. That may not be as interesting, but you have to throw it in order to make it work. So orthogonal coding gives you a chance, or that might be the one that you're really interested in, and you can do the other ones as well in order to make it work. It's just another way of coding the data. If you've got those specific sorts of comparisons you want to make between the groups. Actually, Shifan, if you can write a note for me. Yeah, I want to kind of twist this next time and maybe even leave the notion of uncorrelated, make it a minor trivial point. Less important than, I think it's the comparisons that's the really interest. That's a more fundamental level. That's what makes it interesting. It's those specific comparisons of your groups that you want to do. And this gets at it in a legitimate way. Okay? Similarly, you could do another one. Let's say I want to look at different types of schools. Public, kind of a general public school, a public charter school, a private non-parochial school, or a private parochial school. This is kind of a classic example of why, because you can kind of see there's public and private, and there's parochial, non-parochial, there's kind of, you can see kind of how you might group it. And so one question might be, well, among the public schools, how does a general versus a charter school work? Among the public schools. Among the private schools, how does a non-parochial versus a parochial school work? That's another question. And then my third question might be, how do the public schools compare to the private schools? So you combine each group. That would be another good example of why you might want to do orthogonal coding. Dummy coding won't do that. Effect coding won't answer those questions. So again, let the question drive how you code the data. The kind of related to all of this, as we're getting ready to wrap up that chapter, another thing we've touched on it a little bit, but just to kind of summarize it all in one place, unequal ends. If you have equal ends in every group, life is very simple. But if you don't, you just have to keep track of what's happening. For dummy coding, another reason I think we like dummy coding, equal ends, unequal ends, it doesn't really change the coefficients, how you interpret them, or how you'll talk about them. Nothing really changes. The coding's the same. It's still all the 0, 1, 0, zeros and ones. The interpretation is exactly the same. We talked about for effect coding, keep in mind now you've got to talk about the mean of the means. The intercept isn't the grand mean anymore. It's the mean of the means. That's kind of the big distinction you need to keep track of if you're doing effect coding. And orthogonal coding, if they're unequal ends, it gets even more complex coming up with the right values. I'll just tell you, you're not coding them 0, 1s or negative 1s. It's different. You can have fractional values and stuff. It's much messier to come up with a way that, because remember, you still have to make sure whatever you end up with is describing what school type or kind of race, ethnicity. It's got to work in that global variable. So it gets very complicated if you do that. There's rules you can do, but it's complicated. Finally, the book just talks briefly about criteria.